We are the PIC method group at the University of North Alabama. Our industrial liaison this semester is Dr. Sara del Valle at Los Alamos National Laboratory. Our project this semester is forecasting Zika Virus Disease in Brazil, a comparative analysis utilizing Google Trends and Wikipedia. There's a current need in our world to predict disease outbreaks before they actually occur, so that once they do, we can be prepared and better combat them. Our goal is to determine whether or not you can use internet data to then forecast diseases in a specific area around the world. We use data obtained from Wikipedia and Google Trends to then produce linear models to monitor and forecast the recent outbreak of Zika in Brazil. The Zika virus was first isolated in the Zika forest of Uganda in 1947 in a rhesus monkey. Periodic outbreaks have occurred throughout Africa and Asia in recent decades, though, with the most recent occurring on Easter Island at a festival in 2014. The disease was then carried from the festival to the South American mainland, and the current outbreak extends as far south as Paraguay, but reaches as far north as Mexico. Symptoms of the Zika virus include fever, red eyes, joint pain, headache, and rash. It is a very flu-like disease. Brazilian health authorities have, though, noticed a link between Guillain-Barré syndrome, which is an autoimmune disorder. It also is linked to microcephaly in newborn babies. Vectors of transmission for the Zika virus include the Aedes mosquito as well as sexual transmission.
In a paper by Generis et al., a method for the monitoring and forecasting of disease using Wikipedia data is put forth. The method was applied to 14 different disease locations and linear models were produced for each. Adjusted R-squareds from 0 to 1, which is a measure of how well historical data is replicated by each model, is reported for each disease location. The method is as follows. First, obtain Wikipedia article access counts from relevant articles for a particular disease, keeping in mind that Wikipedia does not aggregate data geographically, though language may be used as a proxy. For each article, calculate a Pearson's R against historical data and list the absolute value of R in decreasing order to obtain the top 10 articles. Use these top 10 articles to create multiple linear regressions for the disease and report an adjusted R-squared for each model. Seen here is Generis et al.'s model for dengue fever in Brazil in 2010 to 2013. As you can see, the historical data, being the blue line, is well replicated by the orange line, which is their model, with an adjusted R-squared of 0.85, which is quite high. The model is also forecast plus or minus 28 days, which means the article accesses are shifted forward or backward in time to create the forecast. The forecast's adjusted R-squared remains quite high for all models. Being that dengue and Zika share similar symptoms and the same vectors, and because of the success Generis et al. Had with the Brazilian dengue fever model, we believe a Zika model is well justified. To create the Zika model, we have taken health map data between September 6, 2015 and April 9, 2016, which to be our confirmed cases, and we have looked at article access counts from 31 relevant Portuguese Wikipedia pages, with Zika fever being the main article. The Wikipedia pages are between August 2nd, 2015 and April 9th, 2016 to allow for up to 35 days of forecasting. We've also looked at Google Trends data between the same date range, which has the added benefit of being location specific. Google Trends provides two different types of data for us, the first being a string specific search, which we have labeled Google Terms, and the second being an aggregate of several strings, which we have labeled Google Topics.
Here we have the model that was produced from the Wikipedia data. The solid purple line represents the ground truth data obtained from healthmap.org and represents the number of cases by the axis to the left. The dotted yellow line represents the model that was reproduced from the Wikipedia data. And the gray lines represent the first 5 of the top 10 articles and are represented by the right y-axis as a search index from 0 to 1. As you can see, this model has trouble predicting the earlier cases due to their low volume. As we can see here, this line here, as it's very low, the model tries to compensate for this and struggles. As we can see, this first spike here, it has a lot of trouble with predicting, but as we move into 2016, the model actually performs very well at predicting the data, trending with this spike here, as well as predicting these 2 spikes here. This model produced a nowcast R-squared value of a 0.3421. When we say nowcast, we mean that the data that was retrieved from healthmap.org is matched exactly with the Wikipedia data in terms of date. Here we have the Google Terms model. This model produced our best nowcast R-squared value of a 0.5703. The only time this model has trouble, other than the earlier data in the late 2015, it doesn't predict this peak here, but it does trend very well with these 2 peaks here, and it's even seen in our 2 search terms here. This is our Google Topics model. This model struggles very much in trying to predict the late 2015 data and probably contributes to its low adjusted R-squared value. But as we see moving into 2016, this model actually does perform very well, even predicting this peak here, which we didn't see in the Google Terms model. This model gave us an adjusted R-squared value of a 0.3787. One of the advantages of using Wikipedia is that we can aggregate data by day with Wikipedia, whereas with Google Trends, we can only aggregate by week. So if we have 5 weeks of data, we can only produce 5 models with Google Trends, whereas with Wikipedia, we can produce 35 models of forecasting. As you can see from this graph, Wikipedia performs less well at the early forecasting and nowcasting, but as we move towards the far field of forecasting, specifically at 25 and 26 days, and then again at 34 and 35, we actually do produce R-squared values that are well over 0.6. Here we report the adjusted R-squared values for the nowcast and the 1 to 5 week forecasts for Wikipedia, Google Topics, and Google Terms. We also report the best R-squared values for Wikipedia between weeks. As you can see here, the best nowcast was Google Terms, and as we move towards the later forecast, Wikipedia does perform better. In conclusion, it seems that Wikipedia is more apt at late forecasting, whereas Google Terms and Google Topics perform better in the nowcasting and the earlier forecasting.
So for our future work, we would like to create a single model utilizing both the Wikipedia and the Google Trends data in hopes that this will give us a better result. We would also like to update our models as most recent data becomes available. We would also like to generate models for other affected countries using Google Trends, since Google Trends allows us to search specifically by location. We'd also like to expand our list of relevant Wikipedia articles in Google searches instead of just choosing articles that are 1 click away from the disease page. We also want to include articles that are 2 to 3 clicks away from the disease page. We'd also like to incorporate other sources of internet data such as Twitter and Facebook and other search engines. We'd also like to use a rank correlation coefficient such as Spearman or Kindle, which ranks the data ordinally and is less sensitive to outliers, to choose the top 10 article searches. This would be good since our data is relatively flat at the beginning and tends to spike towards the end. Here, we use Spearman's rank correlation coefficient as opposed to the Pearson to pick the top 10 Wikipedia articles. As we can see, this yields a better nowcast and a more consistent first few days forecast. We'd also then like to see how it looks with the Google data. PICMath is the program of the Mathematical Association of America and the Society for Industrial and Applied Mathematics. Support is provided by the National Science Foundation. We would like to give thanks to our faculty members here at UNA, Dr. Lee Raney and Dr. Jillian Stupiansky. We'd also like to thank our industrial liaison, Dr. Sara Valle, at the Los Alamos National Laboratory. We'd also like to give special thanks to Dr. Jeffrey Fairchild and Dr. Reed Pretorsky at Los Alamos National Laboratory.